we're going to continue with neural networks. In particular, we'll talk about networks with multiple dimensions, and we'll go over overfitting with respect to adding more neurons to your network. So we have our standard picture of a neural network. In the last video, we only discussed the case where we had a one-dimensional input. So in this video, we're going to go over the two-dimensional input example, and everything that we learn here extends to d dimensions. Just like in one dimension, we'll have a two-dimensional data set. And looking at this data, you can see we really can't use a line to separate this data. So we have this line, and that doesn't work. And how about this line? No, it doesn't work. It's pretty easy to verify that we can't use a line to separate this data. And this is actually called the XOR problem, and it's a very famous problem in neural networks. So what we're going to do is we're going to use the convention of coloring the particular region, decision region, with a color. So for example, in this part, anything in this red region will be classified as class 1, and anything colored blue in this region will be classified as class 0. So let's see what happens when we try a different number of neurons to formulate a decision function. So here's a previous example where we had a linear classifier, and basically we have a surface and we can see the height. So anything in this region will be classified as 1, and anything in this region will be classified as 0. And we can see the red points in this region are correctly classified, and everything else is incorrectly classified. Here's another example, and in this example, we actually used 3 neurons. And as you can see, all these samples are misclassified. Now let's see what happens when we increase the number of neurons. So in this example, we have 4 neurons. And we see that these samples are correctly classified, these samples are correctly classified, and these samples are correctly classified. So it seems like the more neurons you add, just like in one dimension, you can build more complicated functions. So here's a decision function, and as you can see, everything is correctly classified. Basically, we don't have to change our neural network module or class, but in the constructor, we basically have to specify the number of dimensions. Similar with the sequential modules, so we just have to change our first layer, the number of input dimensions equal to 2. And in this case, we only have 2 neurons. So the problem with adding more neurons is overfitting. As we discussed, we can construct an arbitrary function with a neural network of arbitrary dimensions. But the more dimensions and more neurons require more data. And we also have the problem of noise. So here's our standard neural network with m equals 4. And let's make it a little easier to see and get rid of the parameters. So in the class constructor, we simply specify the second argument, the number of neurons equals 4. And here's an example, the number of neurons equals 5. In the object constructor, we simply specify the number of neurons is 5. So it seems like if we can construct an arbitrary function, why don't we use the maximum number of neurons? And let's show the problem with that with an example. Here's an example of a decision boundary we'd like to create with a neural network. And here are some samples that generate this decision boundary. But it turns out, in real life, we have noise. So here's an example of a typical data set that we might see. And as you can see, although the majority of the red points are in this region and the majority of the blue points are in this region, there's a lot of noise which causes some kind of overlap. And of course, this is an extreme situation. So let's see what happens when we use too many neurons to formulate the decision region. So here's our actual decision region, and here's the decision region using our noisy data set. And as you can see, a lot of the samples are misclassified. For example, we have blue portions on this side and some red portions on the other side. So of course we can get more data, but this isn't always the case. So it turns out the number of neurons is actually a free parameter, and we can use validation data to determine the optimal number of hidden neurons, and we can also use regularization. And in this course, we're going to only cover one type of regularization called dropout. And that's it for this section.